Hello, my name is Cruz. I am a student at the University of Houston downtown, and my advisor for this research project was Dr. Koshkin. My project is over squaring a circle using mechanical curves. So the contents of my presentation will be straight edge and compass constructions, as well as how to construct the quadratrice, and then quadrature and the logical circularity behind it. So with straight edge and compass, these are tools that ancient Greeks heavily favored. The straight edge and compass is something that they used to do their math. Basically, it's a tool that helps you make circles and helps you do perfect straight lines. With those two tools, Euclid was able to write the elements. This is a combination of 465 constructions and demonstrations, all cycled into one book, one easy to access place. Euclid basically changed the course of mathematical history by doing that. A few examples of what's in the book is transporting and dividing segments, erecting perpendiculars, drawing parallel lines, and bisecting angles. So I have a few examples of those. These are all things that you could do with just those two tools, the straight edge and compass. Now with those two tools, they were able to solve a lot of proofs, they were able to solve a lot of geometrical problems, but there were always three classical construction problems that defined all attempts to solve with the straight edge and compass. Those three problems are as shown, which is cube duplication, angle trisection, and circle quadrature. My presentation focuses heavily on circle quadrature, although mechanical curves are also very good for angle trisection or cube duplication. We can solve all three of these problems. But circle quadrature remained defiant the longest. This one, it wasn't until recently that we discovered it could not be solved, but we'll cover that a little later. So what are mechanical curves? Well, these are a few examples. We have the quadratrice, the Archimedean spiral, the cycloid, and the helix. The definition of a mechanical curve is just basically that it is made with motion. So all of these curves are made with uniform motions, at least a combination of two segments in uniform motion or more. The quadratrice is the one we will focus on specifically. The original name was trisectrice, and because it was originally used to trisect an angle, it wasn't until later on that Dinostratus was able to find how to square a circle with it. It then became known as the square-forming curve, which is how we got the very creative title quadratrice. It literally translates into that, square-forming. So the genesis of the quadratrice requires two uniform motions, one linear and one rotational. As y'all see on screen, if you have a square ABCD, DC falls to AB at the same rate that AD rotates into AB. The intersection of those two segments in motion trace the quadratrice. The final point F on AB cuts that segment into the ratio that we are looking for, which is 2 to pi. That ratio is very important, so keep that one in mind. Now, how can we actually square the circle? So using the segment AF that we produced on the previous slide, we can make another segment that is equal to 1/4 of the circle's circumference. So all we do is we erect a perpendicular on F equal to the length of the radius of the circle, and then we connect those dots to make the line, or the perpendicular on B, which is equal in length to pi r over 2. You can then scale this segment to rectify any circle of any size of any radius. Once we have that segment, we could use that segment to create a rectangle. So if we know the side is pi r over 2 and we create a rectangle with the second side that is 2r, the area of that rectangle would ultimately be pi r squared, which is equal in area to the circle. Then we could use that second picture on screen is called the mean proportional. We could use the mean proportional, which is inside of Euclid's elements, to find a square with equal area to the rectangle. And then ultimately, we have squared the circle. Now there are two objections to using mechanical curves. The first objection is that synchronizing the motions requires the use of pi. If we have knowledge of pi, then we could just circle the square directly. The second objection is a little stronger. That is, suppose the motions are synchronized, then we are able to do that. The final point of the quadratrice still requires us to use limits to find, because at the end of those two segments in motion, they become the same line, and ultimately there is no point of intersection anymore. So to find that last point, we have to use limits. Now that leads us to a logical circularity. which is why Descartes, who is a famous mathematician, originally rejected these curves, as they did not meet his strict requirements of algebraic or geometric. Apollonius, Archimedes, and Hipparchus utilized these mechanical curves. In ancient Greece, they utilized it to square the circle or even angle trisection. And it wasn't, like I said, it wasn't until recently, 1882, that Lindemann's proof of the transcendence of pi, that it became known that straight edge and compass solutions to quadrature were indeed impossible. So we have mechanical curves that can yield the solution we want, that we do not accept. And then we have tools that we do accept, which is the straight edge and compass, that cannot square the circle. This is due to constructible numbers, which is what my research has mostly focuses on. Descartes basically found a way to take geometric objects and turn them into algebraic numbers. Gauss went the other direction, where if you had a algebraic number, you could turn that into a geometric segment using straight edge and compass. Ultimately, all constructible numbers are algebraic. So my personal conjecture is that pi is not straight edge, compass, or angle sector constructible. If this is true, this would imply that the circle cannot be squared with the quadratrice or similar mechanical curves. So after 2,000 years, quadrature still remains defiant. Although proof of our conjecture is probably beyond reach at this point in time, we hope to prove it conditionally on a famous conjecture that is believed by many number theorists, which is the Chanuel conjecture. But yeah, and so these are my references, and if you guys have any questions, I'll be here to answer them.